I guess coughing. Force, right? And there's other videos on this, but this is kind of basics of like where we get force from. So this is less, at least this video is less like calculations and more like fundamentally what a force is. And to understand force, you really got to understand acceleration. Well, to understand acceleration, you got to understand velocity, and to understand velocity, you got to understand displacement. So it's kind of giving you the basics of what those things are. Okay, in this video, I'm making this one because hopefully seeing it from different perspectives, from a calculation perspective, and then from kind of like a conceptual perspective, hopefully makes it all click. Okay, so I got this great picture of, for those who understand the joke here, these three different nerdy things that I like: Star Trek, Lord of the Rings, and Harry Potter. Nice combination there. So anyway, all right. So force, you say, what is it? We think of a force as basically a push or a pull. Okay, I mean this is really a good way to describe it. Pushes or pulls or forces. Okay, they cause things to accelerate, aka get faster or slower. Technically, changing direction is also an option, but that also involves a change in velocity. So it's kind of changing velocity, changing speed is really the main thing here, and it's either getting faster or slower. Okay, acceleration is both. You might say, well, isn't that deceleration? To slow down? It's a common way of saying it, but technically both getting faster and getting slower are examples of acceleration. Okay, we'll talk more about this later, but the idea is that force requires energy. If I'm causing something to speed up or slow down, it requires energy. Okay, and energy is the ability to do work, the ability to move something. I mean, it's kind of silly because you're like, isn't that kind of circular? Sort of, kind of, but energy is a different quantity than a force. Okay, there's energy that can be used to do things that are not forces, right? So energy is like the currency that lets you do a force. Okay, you run out of energy, you can't do a force anymore. Okay, if that kind of makes sense. All right, so how do we think about this in a more scientific way, right? Well, we can thank for that good old Isaac Newton. So this little picture here, you may have heard the story about Isaac Newton and how an apple fell on his head. People knew about gravity, obviously, well before Newton was alive. But the idea here is that he got the idea of, like how quickly an apple falls, right? It accelerates, it gets faster as it falls, and gave him the idea for how to model acceleration, how to model objects in motion, okay? And this picture here, this is allegedly the apple tree. I believe at Cambridge, I think. Could be Oxford. I don't remember. I think it's Cambridge. I think he was at Cambridge. Anyway, university in England where he allegedly had this inspiration. You can see it fell down. There was like a windstorm and it fell down a couple years ago. Anyway, that's not why we're here. What is Newton trying to do here is trying to give a mathematical representation of gravity. Okay, make it quantitative, right? Measure it out. Very important part of science. And this is pretty good here, where if you take a physics class, you're going to learn very quickly that a lot of science is a math class in disguise, right? And that can both be a good thing if you like math or a very scary thing if you're afraid of math, okay? So we're going to use math. Gravity, of course, causes things to move. Ergo, we would think of it as a force, right? Causes things to get faster or slower, sure. And then how do we come up with a way of representing it? We have this equation. F equals ma. Force is mass times acceleration, okay? The reason this is important to understand, of course, is because this explains a lot of behavior of objects, okay? Objects in motion, that is. Forces cause things that have mass to undergo acceleration. That is what this equation is basically saying. If I have a force, it will cause an object with mass to undergo acceleration, okay? If I have a negative force, right, you say negative. Yeah, negative could be, for example, pulling, right? Positive could be pushing, right? Direction is how negatives and positives play in here, okay? We could have forces where if it's going up, it's positive. If it's going down, it's negative, right? We have different ways of representing this. But fundamentally, forces cause objects to accelerate, okay? Note the units, right? We need to have the correct units. This is hopefully something that you're comfortable with, but you got to make sure you're plugging in the right units. If you plug in the wrong units, it won't work. It will break, and you got problems, okay? Let's break down these various terms. Mass, of course, this is basically, I say, the bulk of a substance. It's the atoms, it's the material that makes up any substance you can think of. Okay, pretty much anything you think of as mass. The exceptions would be things like energy, like like if you think about like electricity, that really isn't mass, right? Wires don't get heavier when electricity runs through them. Okay, um, light does not have mass, right? Like the light coming out of this is not hitting me and hurting me because there's no mass, there's no momentum being conveyed. Okay. We often think of mass and weight as the same. They are different. Mass is independent of gravity, whereas weight depends upon gravity. So if I go to the moon, I still have the same number of atoms in my body. I still have the same mass. But if I go to the moon, the force of gravity is much weaker, which means I weigh less. And yes, I will feel lighter, literally. And if you're like, I don't believe you, well, you don't even need to go to the moon to do this. All you got to do is go to a swimming pool or a bathtub, I suppose. You feel lighter in water, right? Because the water is basically pushing up and basically cushioning some of the gravity, if that makes sense, which means you feel lighter. Okay. There's other examples we could do, but that's the simplest one. Okay. Yeah, so this idea of mass, hopefully you're saying, I kind of get it. These atoms don't let other mass go through, so I can't, I can't do this because there's stuff in the way. Whereas light, right, could easily go through this. Okay, and you say, no, I can block light out. Yeah, but you got to think about why is that? Okay, like put my hand up to the light, okay, and you can see light still finding its way sort of kind of through my hand. Okay, energy can still find a way. It might get attenuated, it might get weaker, but it still can find a way through. Okay, a little bit. That statement is not perfect, but it works for the most part. Okay, acceleration. This one is much harder to understand. Okay, acceleration is getting faster or slower. You say, that's easy. Yes, but like visualizing it, seeing it is difficult. Okay, you get in a car, you hit the gas pedal, you hear and you hear your car start to go faster, right? It's accelerating. Yay, hit the brakes. Car screeches through a hole. Acceleration, getting slower. Yay. Change in velocity. This word right here is the key concept. If we're going 60 miles an hour, I hit the brakes. I'm going 40 miles an hour. I decelerated, right? I lowered my speed to 40. Okay, I changed my velocity. If I go from 40 to 60, I've accelerated. I have increased velocity. That's a change. Okay. To understand these, you really got to break down each one by itself. So let's take a look at now velocity. Okay, velocity is a change in what's called displacement. And then you say, well, what's displacement? And that one might be a little bit scary. Displacement is basically how far you've gone, like the distance you've traveled. Okay, so you're like, well, that's not that bad. It isn't. Not right this second it isn't, but it'll be kind of tricky here in a second. Okay, so hopefully it makes sense. So let's take a look. Right, I have these three graphs showing you how it can be kind of tricky to visualize these things. Okay, so if I have a graph of displacement over time, right? This graph, of course, is saying if you look at this rate here, it's nonlinear. There's a curve. In this case, we are getting faster. Our velocity is increasing. Okay, every second I'm getting faster and faster and faster. That's acceleration. So you say, cool, right? That's not that bad. This is linear, okay, which means I'm going up at a constant acceleration, a constant rate of increasing my speed. So my acceleration is a flat line. That does not change, right? The acceleration is staying the same in this case. It can get messier. If acceleration was increasing, well, then velocity would be increasing at a nonlinear rate, and then displacement would be increasing at a much faster pace. Okay, it gets kind of messy, but hopefully it's kind of making sense. Okay, so let's talk about displacement more in depth. So hopefully it makes sense. Displacement is how far you've gone from a point. Okay, when I say a point, I mean like a point on a map. Okay, to make it easy, imagine if you're in New York City and you want to go to Boston. Well, to get to Boston, you got to go north and you got to go a little bit east. Okay. The idea is that I could travel, if I went from New York to Boston, right? I could draw a line. I can't literally drive through water, but what I'm trying to say is imagine if I flew on a plane, for example, right? Bird's eye or what is that? As the crow flies, that expression. The idea is that that's a distance, and that distance is always positive. It's always going to be some number. Let's say it's 300 miles away, right? I have to go 300 miles, okay? Whether I went from New York to Boston or New York to Atlanta or New York to D.C. or New York to Los Angeles or whatever, right? The distance is always positive. But the idea of the set point is that if I imagine New York as the center, if I can get this right, the center of a graph, right? The origin of the graph. If I'm going up, that would be positive displacement. If I'm going south or down, that would be a negative displacement. So now we have numbers where we're using positives to convey direction and negatives to convey the other direction. Okay? This is called a vector, all right? Vectors are, I'm not saying they're super hard to understand, but basically it's a number with direction. Okay? If it's positive, you infer, oh, that must be north, let's say, and then the negative would be south. Okay? If I'm going east or west, maybe east would be positive and west would be negative. It's like a number line is how you should think about it. Okay? So you can have negative displacement, and it implies which direction you've gone. Okay? And yes, it can get messier when you get to two-dimensional vectors, so as in like northeast, southwest, right? We can get into that, but for now, keep it simple with one-dimensional, right? East or west, north or south. Okay? This is again a vector. Okay, number with direction. In general, the keyword is general. If you see a number in science that's negative, it often means it's a vector. Okay, there are some exceptions, but that's a generally good rule. Okay, like temperature is a good example of that. Temperature is not a vector. Okay, if you use Kelvin, then it isn't, because 0 degrees Kelvin is the lowest temperature. So that's why we should use Kelvin in science. But anyway, displacement. We use the letter S for displacement. Believe it or not, that's kind of weird. I had to look it up because I was like, why is that? Spatium, which means the space between. So it kind of makes sense. But again, you're like, who knows Latin anymore? I'm kind of with you. It's a fun language, though. Very interesting. What else we got about displacement then? Make sure you know the difference between displacement and distance. Okay, they're very similar, right? You say I travel 600 miles from Houston, Texas to St. Louis. I have no idea if that's true, by the way. I'm just picking numbers, right? You say I'm traveling that distance, right? It's positive. I can't go negative distance. But displacement can be negative. So north to St. Louis would probably be positive. If I was in Houston and I drove south to, let's say, Guadalajara, right? Let me try that again. My voice kind of didn't say it right. Guadalajara, right? The capital of, what is the state? Jalisco, right? Which is in Mexico, right? So the capital of Jalisco is Guadalajara. If I went south, I might call that a negative displacement. Okay, positive north, negative south, negative west, positive east. That's how you can think of it right now. Okay, hopefully you're saying, I get it. I have this very beautifully drawn picture. You can see how artistic I am, quote unquote. But here, hopefully you can picture it, right? Starting point, origin would be a good place to pick. And you say if I go, let's say, to the east, that would be positive because I'm going along the positive x-axis. If I went west, that would be negative because that's along the negative x-axis. Okay? So again, when you look at this, right, think north or up, positive, down, south, negative, left, right, you get the idea. Okay? Hopefully making sense. Okay? Displacement does not care about the path you take. If I were to drive or take a plane, straight line, get on from New York to Boston, get on the plane, fly straight there, that displacement would just be, hey, how far have I gone? Right? Doesn't make a difference what route I took. Okay? Whereas distance does care about the route. Okay? If I said, hey, I want you to walk from here to, let's say, I don't know, California, right? And you say, I'm just going to walk a straight line. That's the fastest way, right? That's the quickest. That's the least distance, right? If I said walk and, I don't know, go to every single gas station along the way, I mean, you're going to have to make a lot of detours, right? You're going to go up, down, north, right, all over the place. You're going to go a lot more distance, but believe it or not, your displacement would be the same because you started here and you ended here, okay? Displacement only cares about that. Displacement does not care about the path that we take. Hopefully that makes sense. Okay. Looking through some displacement problems. Let's take a look at some of these. Okay. 45 kilometers east in 20 minutes. What is their displacement? We only care about how far we've gone. That's all. 45 kilometers. Doesn't matter how fast. That's velocity. We're not there yet, right? You say 45 kilometers east, positive 45, right? If I had, let's say, I go 45 kilometers east and then I turn around, I go west for 30 kilometers, what's my displacement? Well, it's easy. You would say 45 is positive. I turn around, my direction has changed. Now it's negative. I go negative 30, positive 45 plus negative 30, positive 15. Okay, if you look at that, you're like, I basically started here, went here, turned around, ended up here. That's your displacement, 15 kilometers. The distance you've traveled would be 75, right? If your car, you're driving it, you look at your odometer, the thing tells you how many miles you've got, that would read 75 kilometers, right? But the displacement would only be 15. Okay, and I got more here, right? Car travels north of 40, turns around, goes south for 60. So this would be positive 40 plus negative 60, or 40 minus 60 if you want to shorten it, which means we've gone 20 south. My displacement would be negative 20. Okay, negative 20 kilometers in this case. Okay, and again, these visualizations, hopefully you're saying, oh, that's not that bad. Okay. Again, we can have x and y components. If we have a diagonal, what I would say, again, if you're taking this, if this is like a freshman level physical science class, maybe your teacher wants to do that. I mean, I say kudos to them. Kudos is Greek for glory, right? Glory to them, because I would very much like to do that kind of stuff, but I got to make sure we're keeping it appropriate to the age, appropriate to the course, okay? So I think what we'll do is we'll call it quits here for displacement, okay? Because we're getting into velocity in the next video, okay? So you can see here, if you were ambitious, if you're like, I would like to try one of those 2D, I want to try one of them, you can see here what it would look like, right? And you can get this picture of, it's diagonal now, and I have components, my x and my y, okay? So if you're interested in that kind of stuff, happy to take questions about that and give you the information you might need. All right? Well, anyway, have a great rest of your day, and the next video on velocity. Have a good day.